Uh, Hi everyone. Am I audible?
Yes, you're audible.
Okay. Uh, so is my screen visible to you all? This contest page.
Yes, it's visible.
Okay. So we'll be waiting till uh, one more. We'll be waiting for 1 more minute, and after that we'll start. Okay. So now we will be starting. So welcome to the Leetcode week discussion for Leetcode weekly contest 334. And in today's contest, there were four problems. We'll be discussing all four of the problems one by one. So the first problem was left and right sum differences. And basically, the problem said that given a zero indexed integer array nums, find a zero indexed integer array answer where answer dot length is equal to nums of length and answer of I is equal to absolute difference of left sum of I minus right sum of I, where left sum of I is the sum of elements to the left of I, and right sum of I is the sum of elements to the right of I. Okay. So let us understand what this problem means one time, and after that we'll talk about how to implement it. So firstly, we are given one vector or one array, and let us say that the size of this vector is n. Okay. So what we have to do, we have to return one answer vector or answer array of size n such that in it all of the elements are equal to this value, left sum of I minus right sum of I. And what is the left and the right sum? So let us consider this 10. So for this 10, since there is no left value, so it left sum will be 0. For towards it right, there are three values, 4 plus 8 plus 3, which is equal to 4 plus 8, 12, 15. Okay. For the next position, for this 4, towards it left, it's 10, and towards the right are 8 and 3, minus 11. Now for this 8, it would be 10 plus 4, 14. 14 would be the left sum, and the right sum would be 3. And for this 3, the left sum would be 10 plus 4 plus 8, and the right sum is 0, since there is no element towards the right of it. Okay. So the left sum would be 10 plus 4 plus 8, 22 minus 0. And so our answer would come as 15, 1, since 10 minus 11 is minus 1 and absolute value of minus 1 is equal to 1. 14 minus 3 is equal to 11, and 22 minus 0 would be equal to 22. So this would be our answer for this test case. And if we match it, it is coming the same. Okay. So in this problem, what happened was that the constraints given are small, and we can run a brute force type thing. We can run a brute force. However, over here, what I won't be telling you the brute force. Instead, I'll be telling you the optimized approach. So in this problem, since n is small, we can apply brute force, but I'll be telling the optimized method. So the optimized method relies on finding the prefix and the suffix sum. In fact, if we find only the prefix sum, we can also use that. So if we find the prefix sum, then we can use the prefix sum to answer our queries. And how can we use it? So let us suppose that we have to find the value of the left sum for any element I. So the left sum of I would be equal to the prefix sum of I minus 1. Okay. So is this part clear that the left sum of I would be equal to the prefix sum of I minus 1? Prefix, okay. Yes, this is the prefix sum and suffix sum concept. Okay, so the sum and suffix sum concept is very like intuitive, and what we do is, let us suppose there is an array of size 3, A, B, C, D, A, B, C, size 3. So we make a array of size 4 or n plus 1, where the first element is 0, the second element is A, uh, meaning this element. The third element would be A plus B, and the fourth or the final element would be A plus B plus C. So, why is this called the prefix sum array? Because over here we are finding out the sum of all the elements in the prefix children. So, for example, for this C, the sum would be A plus B plus C, but for the zeroth position, it is 0. So, is this like clear to you? Why is 0 included? So we include 0 because 0 will make our implementation easier. Like how it will make our implementation easier is because whenever we have a 0, we can say that it is an empty array, and the sum of an empty array is 0. If we don't have a 0, instead we'll have a minus 1, and then we'll have to say that minus 1 is an empty array and minus 1 would be 0. So this is the reason that we use 0. If we don't include 0, then also it will work fine. Yes. 0 is here only to make our implementation easier. Like it will not change the concept as such. Okay. So the left sum of I would be equal to prefix of I minus 1. I minus 1. And the right sum would be equal to prefix of n minus prefix of I. So if you like write down the value one time, you can easily confirm that this will hold true, prefix of I minus 1. And so let me give you an example for this array only. For the second test case, no, the second test case is very small. Okay. So let us see for the second test case. So for the second test case, there is only one element, 1, and its prefix sum would look something like this: 0, 1. Now we'll have to find the value answer for this. So the prefix sum of 1, left sum of this value at index 1 would be equal to prefix of 0, which is 0, and the right sum would be equal to the prefix of n minus the prefix of I, index pre of I, which would again be 0. So the answer would come out to be 0. So let us look at the implementation one time, then this will become clear to you. So during my contest, I have used something which is a bit more complicated. I'm going to make that simple and more related to what we just discussed. Okay, pre of n plus 1. Over here it should be n plus 1. Hmm. Answer of I minus 1 should also be there. Okay, so this is the implementation that I was talking about. What is the implementation? We'll firstly find out the size of the vector which is being sent to us. Then we'll make our prefix some vector of size n plus 1 and generate it as we talked about that pre of I minus 1 plus nums of I minus 1. Then we'll have an answer vector, and the answer value would be absolute. I'm using the inbuilt C++ absolute function, pre of I minus 1 minus, so this is the left sum value and this is the right sum value, and this value is prefix of n minus prefix of I. So is this clear? Prefix of I minus 1 minus, so it is not prefix of I minus 1 minus, it is equal to prefix of I minus 1 minus, and this is the right side value, prefix of n minus pre of I. And the reason it is like that is because we have to find the right sum, meaning the values or the sum of values to the right of it. So prefix of n basically has the sum of all the elements, and prefix of I has the sum of elements till index I. So pre of n minus pre of I is equal to the sum of elements only in the range. Uh, okay. So basically in this problem, we are using two different things. I'll explain one by one both of them. So the first thing is pre of I minus 1. Okay. So pre of I minus 1 is equal to the left sum of I. Left sum. Okay. And the left sum is y equals, meaning all of the indexes which have all of the indexes less than I. So for example, in this array A, B, C, D, these are just variables or temporary like values. If we have to find the left sum of C, it would be equal to B plus A. Okay. And the prefix sum array would look something like this: 0, A plus B plus C, and A plus B plus C plus D. So as we can see that if we find out the prefix sum of I minus 1, then we have found out the left sum of C. Okay. The second part is pre of n minus pre of I. Over here also it is equal to pre of n minus pre of I. Okay. And this is equal to the right sum of I. Right sum. And again, if we take the example of this C, so it would come out to be A plus B plus D plus C, A plus B plus C plus D minus A plus B plus C. And when we will subtract this, we will get D, which is equal to our right sum. So hopefully this is clear to you. Uh, is this clear to you? So I'll be moving to the next problem. If you have any doubt, you can like write in the chat and then we'll discuss it afterward. Okay. So the next problem was about finding the divisibility of an array or a string, sorry, divisibility array of a string. And what we had to do, what we had to find out if the value of a prefix was divisible by m or not. And we were given a word or basically a very large number, and we were given m. And we had to return which of the prefixes were divisible by m. So in such a problem, we use something known as modular arithmetic, modular, and there are some basic operations in mod, and what they say are that a plus b mod m can also be written as A mod B uh, plus B mod M. And right now it isn't making like a lot of sense, but trust me, it will in a second. So let's suppose we have to find out 100 raised to power very large number, like 100 raised to power 100 plus 1, and we have to find this mod 100. So what we can do is we can split it like this, and then we'll have to find 100 mod 100 raised to power 100 mod 100, which would be 0 plus 1 mod 100. So the thing is that using this, our calculations become easier. Like we are able to do everything in mod, and then we don't require very large data ranges. We can use only long, or we can even use integer data type. Otherwise, if we have to use very large types, then our time complexity will also be affected by those data types. So we'll be using these modular arithmetic operations over here, and how we will be using them are, firstly we'll be finding out, we'll be making one variable long val. And what is val? Val is basically the value of any prefix currently. So for example, if our word is like this 9811, and we have to find it mod 100. So at index 1, our value of val would be 9. Then at index 2, it would be equal to 98. At index 3, it would be equal to 81. And then at the final index, it would be equal to 11. So this is how like val would change. Val is basically the value of the prefix till the ith index. And how we will be doing is long val equal to 0 ll. We'll be initializing it to 0. Then we'll also be making a vector int answer, which we would return later on. Now we'll be iterating to the word character by character, and every time we will be finding out the digit at that position. So how we will find the digit is by subtracting the ASCII code of 0. That way we have found out the digit. Now is equal to val into 10 ll plus digit mod m. Why we are doing like this is because let us suppose we have we let us like I try to dry run it once for this example. So initially val was 0. Now we come over here, the digit is 9. So val into 10 plus digit, which is equal to 9. So this way we have got the value for this index. Next time val will be 9 and the digit will be 8. So 9 into 10 plus digit 8, which is equal to 98. After that it would be 98 is now the val. The digit is 1. 98 into 10, 980 plus digit 981. Mod 100, it would be equal to 81. The next time val will be equal to 81 and the digit will be equal to 1. Val into val into 10 would be equal to 810 plus the digit 1, which would be equal to 811, and mod m, that would give us 11. So this is how we are finding out the value of val. Now if val is not equal to 0, then we will be pushing back 0, since we are not divisible by m. Otherwise we will be pushing back 1, and after that we will be returning the answer. So any problem with like this divisibility, find the divisibility array of string. Is it clear? Could you please repeat? Okay. So for this, what we are doing is we are using modular arithmetic, and in modular arithmetic we are using this operation: a plus b mod m equal to a mod m plus b mod m. And the reason we use it is because sometimes we can optimize this thing. so that both of them hold smaller value. For example, if we had to find out the value of 100 raised to power 100 plus 1 mod 100, then we it would make more sense to do this, because then 100 mod 100 would be 0 and we will only have to do 1 mod 100. Okay. Now after that, what we are doing is we are finding out the value of every prefix, which we are storing in a variable known as val. So for this string, the value of every prefix would be equal to 9. Then the next one would be 98, then 81, then 11. And the reason and the way we are coming up with that is by doing this val into 10 plus digit. So it is similar to like if we have to add a digit at the end. For example, if we have 100 and we have to add 2 at the end, meaning we have to concatenate, then we are doing 100 into 10 plus 2. So this is how we are finding out val. Now, if val is not equal to 0, meaning that the value mod m is not equal to 0, then please push back 0. Otherwise, answer dot push back 1. And this is how we are doing it. How 81 and 11 come. So mod m is basic. For this example, I was taking 100 because 100 would like allow us to see better, understand better. So we are clear till here. Like 81, we have to talk about 81. Okay. So 98 into 10 plus 1 would be equal to 981. Okay. Now, what we are doing over here in our code also is we are doing it mod m. So 981 mod 100 is now returning us 81. So this is how we are coming up with 81. And after that for 11, again 81 into 10 plus 1, and we are doing it mod 100. So it is coming out to be 811 mod 100, which is equal to 11. So hopefully this is clear to you. Why 100? So 100 because I was taking it as an example over here. In the problem, if we have to do, we will be using 3, but with 3 it is not very clear. So if you want, I can also do with 3. So initially val is equal to 0 and digit equal to 9. Then the next our value of m equal to 3. So val into 10, it would be 0 plus digit 9. 9 mod 3, that would be 0. Next time 9811. Okay. Next time 0, digit is 8. 0 into 10, 0 plus 8, uh, 8 mod 3, 2. So it would return us 2 over here. Over here, next time digit is 1, val equal to 2. So 2 into 10 plus 1, 21. 21 divided by 3, mod 3 equal to 0. Over here, again 0 comes. Over here, digit is 1. 0 into 10, 0 plus 1, 1. Mod 3, 1. So this is the value of val for m equal to 3. I had taken m equal to 100 for explaining. M equal to 3 in the problem and the code also, we will only be using m for mod. Okay. So let us move to the next problem. Hopefully, like this is, we should use modem only. Yes. Over here also in the code also, I am only using modem only. Like you can see, I had taken 100 because 100 was, I was trying to explain with 100. With 3, we were not getting those many values. It was not very clear. So coming on to the third problem. So in the third problem, what we had to do, we were given a zero index integer array nums. Initially, all the indices are unmarked. You are allowed to make this operation any number of time. pick any two different unmarked indices I and j such that 2 of nums of I is less than equal to nums of j, then mark I comma j. So what we have to do in simple terms is we have to make maximum number of pair such that in each pair the smaller, meaning the minimum of a comma b into 2 is less than equal to the maximum of both of them. Okay, and let me explain this with the example with the test case. So for this 3 5 2 4, we can only make one pair. What pair we can make? We can either make 2 comma 4 or we can make 2 comma 5. We cannot make any other pair. Okay, for the second test case 9 2 5 4, we can make two pairs. So one pair we can make is 4 comma 9 and the other pair is 2 comma 5. Okay, so last time also when we were discussing, I said that whenever we have to find the maximum of anything, a very good clue for us is to use binary search. Binary search. And the way binary search works is by using something known as monotonicity of a function. It states basically that if a function is monotonic, either strictly increasing or strictly decreasing, then we can like use binary search to find the maximum value for that function. And how is this function monotonic? So if we are able to make k pair, then we are surely able to make k minus 1, k minus 2, and k minus 3, and so on pair. So if this condition is satisfied, then we can use binary search. Okay, we can use binary search over here. So is this clear that so we can not for every index. You are right. We will have to sort and we will have to find the maximum value, but not for every index. Let me explain one. So let us suppose that we are making k pair. Okay. So when if we are making k pair, then it makes sense that we will pick the k smallest value, k smallest, and the k largest value. Like if we are making one pair, then we will take the largest value and the smallest value and check those. If we are making two pair, then we will take the largest value and the second largest value. We'll also take the smallest value and the second smallest value. Okay. After that, what we will do is we will be sorting the vector. So the vector will be sorted beforehand only, before binary search. And once we have sorted the vector, it will be in ascending order. 2 3 5 4 or 4 5. Now what we will be doing is that when we are making k pairs, so the kth smallest value will be paired with the n minus 1 minus kth largest value, n minus kth largest value. So what this means is that let us suppose we are making two pairs. Okay, so if we are making two pair, so there will be two small value s1 and s2. Let them be like s1 is smaller than s2, and there will be two larger value l1 and l2. So we will be making a pair of s2 and l2 and a pair of s1 and l1. Is this clear? Like what kind of pairing we are doing? So the smallest one will be in, like this in ascending order. So, for example, if the smallest are like 2, 3, 4, 5, so the largest are also in ascending order. Then the largest, let's suppose the largest are 100, 101, anything. So both of them are in ascending order. The k large smallest value and the k largest values. Okay. Once we have done this, what we are doing is that we are checking that, okay, are all of the k pair eligible or not? What that means is that for all of those k pairs, the smaller value into 2 must be less than equal to the larger value. If it is true for all k pair, then okay, our binary search is cool. We can find for more values. Otherwise, we'll have to reduce the search space. So over here, coming on to the code, what we are doing is firstly we are finding out the size of the nums or the integer sent vector sent to us. Then we are sorting the nums vector. After that, we are finding setting a search space. So what is a search space? Search space basically means that what values the answer can take. So the answer can be 1, the answer can be 2, 3, 4, 5. It can be till n by 2. Notice that I am not writing 0 here because I am initially assuming answer to be 0. So if we want, we can also binary search from 0, but I am saying that no, answer is 0, let us binary search from 1. Now this is very like standard binary search. While low is less than equal to high, int mid equal to low plus high divided by 2. Then what I am doing is I am making 2 pointers. One pointer is at the right and the second pointer is at the left. So the right pointer is at the end at the largest value, and this small pointer or the left pointer is at the uh, sm- kth smallest value. So over here it is mid minus 1. Then I am making a variable bool OK equal to true, which basically states that are all of the pair we are making are good or not. Okay. Then what I'm saying, for int I equal to 0, I less than mid, I plus plus, nums of r minus I is less than equal to nums of L minus I into 2. So if you see, the condition for a good pair is this, and for a bad pair, basically this sign will flip. So instead of like being greater than equal to, it will become being less than equal to, it will become being greater. So if this value, the smaller value into 2 is larger than the larger value, then OK equal to false, meaning that all of the pairs are not good. Now, if OK equal to true, then answer equal to mid, meaning that okay, these many pairs are possible. Let us search if we can make more pair. Otherwise, we can say that no, these many pairs are not possible. Let us search if we can make less number of pair. And the final thing is that we don't have to find the number of pair. We have to find the number of uh, marked indices, which is equal to answer into 2. So is this clear? We can use upper bound to find the 2 into min for every index. This will create a problem. So the problem it will create is like, let's suppose 2, 4, 5, 9. No, 2, 4, 2, 3, 4, 5, 9. Now, if we find out the upper bound for this, 3 into 2, 6. Upper bound of 6 will return 9. Similarly, if we perform here again, it will also give us 4 into 2, upper bound 9. So what will happen is that if we use upper bound, we will be making one element more than a part of more than one pair. Like this is the upper bound for both of them. So that is something that is a problematic thing. So we can't be using upper bound as such directly. We'll be having to use something else. So hopefully that is clear. Okay. We will not. We can also use upper bound, but with upper bound, we'll also have to take care about deleting. So what I mean by deleting is that basically, let us suppose if we have to delete some value, so we will be deleting. Like let us take this thing 2459. In this, then our upper bound of two. Okay, 2, 5, 10, 18. Okay. So in this 2, the upper bound of 2 into 2 equal to 4 will be equal to 5. So if we remove this 5, then our answer will not be able to come nicely. Like we will be able to make only one pair this. But in the optimal answer, we are able to make two different pair. One is of 2 comma 10 and the other is of 5 comma 18. So we will not be able to use it minus minus. Uh, it minus minus also won't work directly. Like the thing is that if you are not, we are not confident about what pair we have to remove. Like if I'm saying that for this, one second, white bag, yes, 2 5 10 18. So for this 2 we can you remove, we can make it a pair with all of these, but for this 5 we can only make it a pair with this. So the meaning is that we'll have to first remove this 5 and then this 2 optimally to get the optimal answer. But if we remove this 2 before this 5, then we will not be getting the optimal answer. So that is why we will not use upper bound, lower bound. We can use the binary search approach. Okay. So the final problem was based on Dijkstra's algorithm of finding shortest path in a graph. And like if you are not aware of Dijkstra's, then this problem wouldn't like make a lot of sense to you. So I'll be explaining it in like 1 minute only, just 1 minute. Okay. So the problem is that we have to find the minimum time to visit a cell in a grid. The problem states we are given an m into n matrix grid consisting of non-negative integers, grid row comma column, representing the minimum time required to be able to visit row comma column. And we are standing at 0 comma 0 and we have to reach 6, the final row or the final column, and we have to return the minimum time of reaching there. Okay. So one second. Okay. So the problem is basically we are given a grid like this, and we have to reach from this first cell to the final cell over here. And what happens is that in each cell has a timer, and we can only reach that node at when the time is greater than the timer. Time is greater than timer. So we can think of this like a door. Like we can only use that door when the time is greater than or equal to the timer. Okay. Now the thing to like there are two observations basically in this problem. The first observation is that we can visit a node any number of time. Like it is nowhere mentioned that we can visit a node only once. We can visit it as many times as we require. So we can visit any node any number of time. Any node any number of time. So this is very important because this allows us to waste the time. Waste the time, and what I mean by waste the time is, let us suppose we reach any node by at time t, and the next node opens at time o. O is greater than t. Then what we can do is we can return back and come back. Like we can make a type of cycle where what we do is we go to the node we were at before this move, and then come back and check again. So we can do this, like we can waste our time. And this for happens because we can visit any node any number of time. Okay. Now the wasting no time thing, how it happens is that let us suppose we are at node any node I, or since this is a graph grid, so it would be a cell x comma y, and we can reach we have to go to x plus 1 comma y. So in one move, what we can do is we can return to x minus 1 comma y. Then in the next move, we can come back again, check back again at x plus 1 comma y. Then again we can return. Again we can do like this. So this is the basic, like this is the main observation of this problem, is that we are allowed to waste the time in this problem. In other problem, if we were like only able to visit one node one time, then we would not be able to waste our time. Okay, so hopefully this is like clear to you that we are allowed to waste the time in this problem. Now if we are allowed to waste the time, then this problem becomes like simple, in the sense that if you know Dijkstra, it becomes related to Dijkstra, and we basically then have to go from 0 comma 0 to grid n n minus 1 comma m minus 1, and in each move we have to make one move, and yeah, we have to make one move to one of the four neighbors. So like if this is clear, then the only thing left is implementation as such. So for implementation, what we will be doing is we will be storing all of the four coordinates or all of the four movement types, meaning going up, going right, going down, going left, in a array of size 4. Then we will be finding out the size of the grid, the number of rows and the number of column. After that, we will be making a visited uh, grid or matrix, in which initially every value will be equal to infinity, because initially we have not visited any cell. Okay, then at 0 comma 0, or the starting position, we will be putting the value 0. Then for implementing Dijkstra's, I use a set. You can also use a priority queue, that will also work. And in my set, what I do is I'm passing three different things. One is the distance or the time. In this problem, time makes more sense. Next is the x coordinate of the cell and the y coordinate of the cell. So these are the three things like what I am sending. And initially at the beginning, Dijkstra will be initialized with 0 comma 0 comma 0, while Dijkstra is empty. Not empty, meaning that the size of Dijkstra's is more than 0. There is one cell which we haven't considered. We'll be doing auto. I am like finding out the smallest distance and the cell from the Dijkstra at the beginning. Next, what I'm doing it like this is Dijkstra's implementation only. You can understand it by like referring to some Dijkstra's tutorial. For int I equal to 0, I less than 4, I plus plus. Then I'm finding out the cell I will be going to, small x and small y. If x is greater than equal to 0 and x is less than n, so this condition is basically for checking if we are inside a grid. Condition for checking inside the grid. Okay. And our next condition will be, so after that we'll be having two conditions. The first condition is that we have visiting late, like the door is already open, and we can directly go there without wasting any time. So this is this case that if the current time is greater than the opening time, current time meaning the time by which we will be reaching, and we haven't considered that new node, then we will be insert doing Dijkstra's or updating the shortened distance to that cell. Otherwise, if x is not equal to 0, or y is not equal to 0. So basically, one more observation that would follow from this is that we are only allowed to waste the time when we are not at the starting node. Why? Because if we are at the starting node, we cannot return anywhere to waste our time. We are stuck over there. For example, if we are at 1 comma 0, we can go to 0 comma 0. But if we are at 0 comma 0, we can't go to 1 comma 0 to waste the time as such. So hopefully that is clear. Else if x is less than equal to 0 and y is not equal to 0, Okay, int difference is equal to grid of x comma y, y minus distance. uh, Next thing is that if difference mod 2, so this thing basically comes because while we are wasting time, it might happen that we waste more time than required. For example, let us suppose that we come anywhere at time 5 and the shop is opening at 7. So at time 5 we are at this node, and at time 7 this will open. So we will waste the one time, go over the previous node at time 6. Then when we return to this node, the time is already 7, and by the time we visit this node it would be 8. So over here this part basically handles this case, and this case is int difference equal to the time of opening minus the distance. And if the time mod 2 equal to 1, meaning that there's an odd difference, then decrease it by 1. Otherwise, let it be the same. And end distance is the time at which we would be moving to that node finally, or moving to that cell. Then this is Dijkstra stuff where we are updating the value of that cell. And finally, if the value at the final row and the final column, that is the final cell, is greater than 187, then infinity, then we can say that we were never able to reach here, -1, and we are returning viz of n minus 1 and m minus 1. So hopefully this is clear to you, like why we are using Dijkstra's over here, and all of this casework, like how we are able to waste the time and why we are able to waste the time in this problem. So since like this is clear to you, I'm guessing that we are through with the problem. And yeah, so if you have any doubt, you can ask. Uh, Otherwise, like you can leave also. Okay, so I'm ending the meeting now.